Geometric proofs and problems, and this is chapter 20E of the textbook. There are two specific types of problems we're going to cover. Often in year 11 and 12, you're asked to prove that vectors are concurrent vectors. If vectors are concurrent, that just means they meet or intersect at a single point, say P in the diagram there. Point. You need to show that this point is common to all of the vectors. The other thing that you also need to show is that 3 points, say A, B, and C. If these points are collinear, that would mean that they lie on the same vector, or they lie on the same line. So to show that 3 points A, B, and C are collinear, this just means you need to show that vector AB and BC are parallel, so in the same direction. If they're parallel and B is the common point, e.g. that B is the ending point of AB and the starting point of BC, this insinuates that vector AC is one straight line with point B in the middle of it. So to show concurrency and collinearity, we often use the fact that if AB is a scalar multiple of BC and the point B is in common, then A, B, and C lie on the same vector or are collinear. Just a quick note before we do the examples. It can be difficult to often draw these situations accurately. So when you do so, don't worry about drawing in your IJ or your XY plane. Just try and include key information and use your diagram as a guide. Also, pay attention to the little things in the questions, e.g. the order that they put the points, the directions that the vectors are in. Example 1. We have 3 points P, Q, R. Notice that Q is in the middle here. They have position vectors little p, little q, and k brackets 2 little p plus little q, where k is a constant. That means the vector from O to point P is vector little p. The vector from O to point Q is little q. And the vector from O to R is the vector that is some scalar multiple of 2 times vector P plus vector Q. When we start to draw this, we just have to be aware that the points O, P, and Q are not collinear. That means the origin, point P and point Q are not in a single straight line with each other. But it does say that we need to find the value of our scalar K, or our constant K, if P, Q, and R are in a straight line. These points are collinear. So try and make your diagram reflect this. I'm going to draw in just a point O, P, and then I'm going to put Q and R as points in a line with each other, but make sure O is not in that same line. That way we satisfy the conditions of the statement. Recall that position vectors will all start from the origin and then go to their respective points, so make sure your arrow for each vector is in that particular direction. We know that P, Q, and R are collinear. Because these 3 points are collinear, vector PQ and vector QR must be parallel to each other, and both vectors have that middle point Q in common. We know 2 vectors, when they are parallel to each other, one will be the scalar multiple of the other. That way we can write, and we know that some scalar alpha PQ has to equal our vector QR if these points are collinear. which they are, is we're going to write PQ in terms of our little vectors QP or K2P plus Q. I know that PQ, to start at P and get to Q, I would have to go negative position vector P plus position vector Q. And then I'm just going to expand here. Notice that QR, we also need an expression for QR in relation to K, little p, and little q. So I know to get from Q to R, I would have to go back down the position vector Q, so negative Q, back to the origin, and then add on vector OR, which is K brackets 2 little p plus little q. Again, we can expand and simplify. So we'll have minus q plus 2kp plus kq, where k is the constant we're trying to find. I'm just going to group the q's together and the k's together. The q's will have minus 1 plus k in bracket times q, and then I'll just still have the positive plus 2kp here as well. Now all you have to do is equate the coefficients. If we equate the coefficients of vector q, we'll get that alpha equals minus 1 plus k. And if we equate the coefficients of p, we'll get that minus alpha equals positive 2k. Now this is nice because we just have two equations. We can solve them simultaneously to find our value of k. To do this, we want to eliminate the alphas in these equations. So I'm going to take equation 2 and rearrange it so it's just alpha equals minus 2k. Then I'm going to plug that into equation 1. Once we do that, we'll get minus 2k is equal to minus 1 plus k. Take the k's to one side and simplify. Then we'll get k equals to 1/3. So we've found our scalar k, and if you want to, I guess, relate this back to your diagram, this just means that OR should be 1/3 of the length of 2 times vector p plus vector q. In our second question, we have a parallelogram with vertex points OA, U, B, where OA can be called vector little a and OB can be called vector little b. The direction here matters. Once you've drawn both of these vectors in, we can use the fact that this shape is a parallelogram. So there are some vectors in here that are going to be equal to each other because opposite sides of a parallelogram are in the same direction and also have the same length. That means BU will be vector A, and the direction here, again, very important, must be in the same direction as OA with your arrows. Vector OB will be the same as vector AU, and both of these thus will be little b. Now we have our shape in terms of vectors. Let's look at the second part of the problem. It says let OM equal 1/5 of A, and MP to PB is the ratio 1:5, where P is on the line segment MB. Now, this is a little confusing. So let's start at the beginning. The point P lies on the line segment MB, where OM is just 1/5 of vector A. So we start at the origin, we go in the same direction as A, but only for 1/5 of the length. So that way we can let vector OM be 1/5 vector A. For the second part of this sentence, we know that we need to draw the line segment MB. I'm going to make this a vector with my arrow pointing towards B. We also know the point P splits this line segment such that MP to PB is length 1 to 5. The whole line would have a total length of, say, 6, because 1 plus 5 is 6. Therefore, MP would be equal to 1/6 of MB, and PB is equal to 5/6 of MB. So I've just split this line up into two vectors. So now the arrows are in, we've got MB and the point P. We've got to prove that MB intersects with OU at P. Basically, we're just trying to say that that point P lies on the diagonal OU. So we need to prove, again like collinearity, that OP is parallel to PU, where P is the common point of both of those vectors. To prove this, again, we say that alpha times vector OP should be equal to PU. So some scalar multiple of OP needs to be equal to our vector PU. Let's start with the left-hand side and figure out what OP is. Because there is a show that question, make sure you do the left-hand side and the right-hand side separately here. For OP, I can start at the origin, go to M, and then go along M to get to P. So OP is equal to OM plus MP. We know OM, because of what we drew in, was 1/5 of A. And we know that MP is 1/6 of MB. Now here's my issue. I need to write MB in terms of just A and B. How can you get from M to point B? I know I could go that MB is equal to M to O, so backward along minus 1/5 A, and then I can plus on OB, which is just vector B. Your next step here is just to explain, expand, and simplify very carefully. When we do this, we get that OP is equal to 1/6A plus 1/6B. So I'm hopeful that alpha times 1/6A plus 1/6B will give me vector PU. So my last thing is to figure out, okay, well, what on earth is vector PU? Try and take the easiest path you can from P to U. So I'm going to go PB plus BU. I know that PB is 5/6 MB, and I know that BU is vector A. This is nice because I already found MB before. Recall that MB was minus 1/5 A plus B from our left-hand side. Again, expand and simplify. Eventually we get 5/6A plus 5/6B. That is vector PU. And we can see that actually, if we times OP by 5, we will get vector PU. Therefore, we can say that indeed OP is a scalar multiple of PU, right? We would just times it by 5 to get PU. This means that the vectors OP and PU are not only parallel, but the point P lies on them, which means these points OP and U must actually all lie on the same vector, vector OU, or the diagonal of our parallelogram. In this way, because point P also lies on MB, we can say that these two lines, OU and MB, intersect at point P.